Okay, good afternoon. My name is Peter Poole. I'm at St. Francis Xavier University, and I'm the regional coordinator for the Atlantic provinces for the 2024 CAP lecture tour. Before we get started, I have a couple of announcements about how the talk will proceed. All questions will be handled at the conclusion of the speaker's presentation and will alternate between questions from those attending in person and those participating virtually. For those attending virtually, please post your questions in the virtual chat at any time. Your questions will be posed anonymously to the speaker by the MC. For those attending in person, please wait until you are called on to ask a question, and then use the mic provided to ensure that those participating virtually can hear it. All students participating today, both those online and in person, are encouraged to remain after the talk and participate in a 15-20 minute informal discussion session with the speaker. We also invite any faculty or other attendees at Mount A to participate as well. Now, it gives me great pleasure to introduce our host for today's CAP lecture tour talk, Professor David Fleming of the Physics Department at Mount Allison University, who will introduce our speaker.
Thank you, Peter. It's my pleasure to welcome everybody to the second talk in the CAP lecture tour series for 2024. My name is David Fleming. I'm pleased to host this talk from the Physics Department at Mount Allison University in Sackville, New Brunswick. We welcome the audience that is participating here in person and also those joining us virtually. This event is being recorded, as mentioned, to be made available later for viewing on CAP's YouTube channel. Just going to advance the next screen, and we would like to acknowledge before we begin that Mount Allison is located within the territory of Mi'kma'ki, the unceded ancestral territory of the Mi'kmaq. Our relationship and our privilege to live on this territory was agreed upon in the Peace and Friendship Treaties of 1752. Because of this treaty relationship, it is to be acknowledged that we are all treaty people and have a responsibility to respect this territory. We would also like to acknowledge that Dr. Di Matteo is speaking from the traditional, ancestral, and unceded territory of the Musqueam people. Just a few notes about the CAP, the Canadian Association of Physicists. This lecture tour is sponsored by the CAP Foundation and the CAP, a network of national scope, which has 1,700 physicists working at universities, companies, and research institutions across Canada. The CAP works on behalf of Canadian physicists to support physics education and research, and sponsors a number of physics activity across the year, including this lecture tour and national research conferences. The CAP also delivers a number of programs for undergraduate and graduate students in particular, including research conferences, physics scholarships and prizes, and a student advisory council. So there's some more information provided there on the range of activities and services provided for students. If you are interested in joining the CAP, please do consider joining if you're a student. If you're not already a student. And it's free for undergraduate students to join the CAP. And for the first year of membership for graduate students, it is also free. So those rates and procedures are outlined here from the links. Okay, so moving into today's talk for the CAP speaker series, today's talk will be about 45 minutes in length, followed by 10 minutes for questions. And if you'd like to pose a question to the speaker, you can type your question into the chat function at any time, and we will look for your questions and ask them at the end of the talk. Following the talk today, all participating students plus any faculty members or others attending at the host department here will have the option to remain for an additional 15 minutes to speak directly with the speaker and ask additional questions about research or related career paths. So for now, it gives me great pleasure to introduce today's speaker, Dr. Olivia Di Matteo, from the University of British Columbia. Dr. Di Matteo's research focuses on quantum circuits and compilation, the application of quantum algorithms to solve physics problems, and the development of open source software and educational materials in the field of quantum computing. Today, Dr. Di Matteo will present her talk entitled An Introduction to Quantum Computing and Software for Physics Applications. Welcome, Dr. Di Matteo. Thank you.
Thanks very much, David. Just gonna share my screen. Can you see my slides?
That looks good. Yes, thank you.
Good, okay, awesome. All right, thanks David for the introduction, and thanks everybody for coming today. It's really exciting to be in, it's an exciting time to be in the field of quantum computing today. So hopefully through this talk, I'll be able to give you a taste of what it's like to do research in that area, and also what it looks like to actually use a quantum computer to solve a problem in physics. But before we even talk about quantum computers, we should stop and recognize the contributions of classical computers to physics, because I don't think we'd be nearly as far as we are in our understanding of the universe without the ability to do very, very large simulations. At the largest scales, like people have used supercomputers to simulate what happened in the early universe, like the simulation of like the formation of stars and galaxies. And at the very, very smallest scale, people have used supercomputers to simulate what happens at the level of like interactions between quarks through simulations of lattice gauge theories. Simulation's important for understanding and predicting the results of experiments, such as what happens in particle accelerators. But the benefits aren't only in one direction. So it's not just that we've used computers to do physics. The requirements of physics simulations have also actually advanced the field of supercomputing itself. So I'm not sure if you can see my cursor, but I have a picture here of a supercomputer called QCDOC. And this machine was actually made specifically to do lattice gauge theory calculations. The nodes in the network are set up in a certain way so as to fit the structure of the problem. And the advances that were made in the design of that computer have propagated forwards to newer models. But now, those simulations I showed, you might have noticed that a lot of them are 25 to 30 years old. And at the time, like those were very, very, very large simulations. But problems haven't gotten smaller over time, problems have only gotten larger. And so as we move forward, we're going to need to make computers more powerful. So there's a couple different approaches we can take to do that. Now, all of our computers today are generally transistor-based, and there's transistors sitting on an integrated circuit. And if we want to make computers more powerful, we can put more transistors on the same chip. That generally involves making transistors smaller, packing them more tightly so that we can fit more of them onto that chip and add more power. So that works. That's one way of making computers more powerful, is just have more stuff. Another thing that we can do is have more stuff in parallel by networking many of these processors together. And using this technique, we've brought ourselves to the point of exascale computing. And by exascale, I mean computers that can do 10 to the 18 floating point operations per second. This is huge. So the largest supercomputer around today is called Frontier. It lives at Oak Ridge National Lab. It's got about 9 million combined CPU and GPU cores. This is enormous, and yet this still isn't big enough to solve some of our problems. But in addition to parallel computing, we can also use special purpose hardware. So probably many of you have a computer with a GPU in it. Maybe you're using it to play video games. The GPU is really good at doing the kinds of calculations that video games need. For example, operations like floating point operations on matrices. But again, even with all of these strategies, we're approaching limitations in how much more powerful we can make our devices. Many of you are probably familiar with the idea of Moore's law. And since about the 70s, since we started really keeping track, the number of transistors that we've been able to put on these chips has been doubling roughly every 2 years, and the corresponding cost has also been going down. Now, we're approaching limits, though, to basically how small we can make these transistors and how tightly we can pack them before we start to see quantum effects actually affecting the operation of these processors. So you can see that this plot here ends in around 2020. There's still been a bit of progress since then, but going even further has required novel fabrication techniques, exploring new materials, and this just in general complicates the process of building better chips. But even if we could build better chips, we're still going to reach another limitation, and that's in terms of the complexity of some problems. There are some problems that just scale really, really poorly. Now, these problems aren't necessarily impossible for classical computers to solve, given enough time, given enough memory, but they're definitely going to be intractable. Like, it's not super useful to solve a problem if we're not going to actually be around to see the answer because it's going to take hundreds of years to run. So this combination of physical limitations as well as computational limitations really necessitates that we think about computing in a different way going forward. And that's where quantum computing comes in. The idea of quantum computing started in around the 80s, where people said, okay, well, we need to simulate these many-body quantum systems. The size of these systems scales exponentially in the number of bodies in the problem. That's really big. But what if we had other quantum systems that could simulate the ones that we were interested in? Kind of gets around that problem of needing exponential space in a large amount of time if we can just use quantum systems natively. So the textbook definition is the study of information processing tasks that can be accomplished using those quantum mechanical systems. And what's been really amazing is that we've gone from this kind of idea in the 80s of doing this to actual hardware that we have today. So this is a picture here of a quantum computing device made by IBM. Now, most of this picture is actually the fridge that keeps the quantum processing unit very, very, very cold. It's sitting somewhere down here. But this has actually become a reality, and we can actually use these devices now to solve problems. So what I want to talk about today is what it actually looks like to solve a physics problem on one of these devices. If you go and look at a physics application paper right now in my field, like 80 to 90% of it is really just figuring out how to use a quantum computer to solve that problem, and not so much about like what the results look like. So in order to get there, we're going to go over the basics of quantum computing, just level the playing field for everybody, give you a sense of what the elementary operations are and what these machines can do. Then we're going to talk about quantum software, which is my area of research. I'll highlight a couple applications along the way in various areas of physics, including one that we worked on in nuclear theory. And then I'll close with a discussion of resources, because there's quite a few misconceptions that I'll address about what it means to like use quantum computers. And one of them is that because they're going to be able to solve things so much faster, that this is going to be like a cheap and efficient process. And in terms of a scaling sense, yes, but just because like the problems are not maybe as big and scale better doesn't mean they're still not big. And the amount of resources you actually need in terms of qubits and time can actually be quite large. So we're going to start though with the basics. Now, we've gotten to exascale computing solely by using computing based on bits. So physical transistors, they have a state that we're going to call 0, a state that we're going to call 1. And basically everything that we do in our laptops, in our supercomputers, in our phones, it's all computing based on bits. So in a quantum computer, we have what's called a quantum bit or a qubit. Now, physically, that corresponds to some two-level quantum system. And this is where I give the disclaimer that I am a software person and not a hardware person. So I'm not going to talk too much about what a hardware description of a qubit looks like, but I do have a couple cartoon representations just so you can get a sense of what they could be. So we need quantum systems with two levels, and those could be, for example, the ground and excited state of an atom or an ion. It could be the spin of a particle up or down. It could be the polarization of a photon. And these are all different approaches that people have actually used to make quantum devices. They all have their own strengths and weaknesses, but the main idea is that you have some idea of a 0, some idea of a 1. Now, in order to actually model this, to do simulations, we need a mathematical representation as well. So mathematically, qubits are represented as vectors in a two-dimensional vector space called the Hilbert space. So we have an idea of a 0, which is just a 1 and a 0, and also a state 1. Now, the big difference between classical bits, which are only 0 or 1, versus qubits, is that qubits can exist in a quantum superposition of those two basis states. So something that's not quite 0, not quite 1, it's a bit of both. Mathematically, we represent this using a linear combination of basis states. And those of you who have taken quantum mechanics will probably recognize this. Like, this is just a wave function. It's a linear combination of basis states. There's going to be some criterion for that state to be valid, for that state to be normalized. And in the case of a qubit, this is a space where the coefficients in this linear combination can actually be complex numbers. And the normalization criteria is that the moduli squared of these numbers has to sum to 1. So quantum computing is all about manipulating qubits, changing their states to achieve a certain purpose. So we need to have an ability to do actual operations on these qubits. So physically, what that corresponds to is actually going to depend on the underlying hardware implementation. But in a general sense, it generally corresponds to like having a physical system applying an electromagnetic pulse of a specific frequency, of a specific duration that's going to affect the transition between the 0 and the 1 state that you want. At a mathematical level, we basically need operations that are going to take these two-dimensional state vectors to other valid two-dimensional state vectors. And there's a special kind of matrix operation. In the case of a single qubit, it's a 2x2 matrix that does this, and it's called a unitary matrix. So unitary matrices might look a bit abstract at first, but again, if you've taken a quantum mechanics course, you might already be familiar with this concept, and you've actually seen a couple of examples. So the Pauli X gate, or the Pauli X operation, it has a computational meaning in quantum computing. And what it actually does is it performs a bit flip operation. It turns the 0 state into the 1 state, and it turns the 1 state into the 0 state. Those of you familiar with computer science and logic gates will recognize this as a computational NOT gate. So it has more meaning than it just has as like the Pauli X spin operation. It also does like a computational meaningful operation. The Pauli Z operation is also a unitary operation that has computational meaning, but it does something that doesn't really have a classical analog like the bit flip does. What the Pauli Z does is it can change the phase or the sign of the coefficients of these amplitudes in the qubit state. It doesn't do anything to 0, but it changes the sign on 1. But you'll notice that both of these operations, they just take one of these basis states to another, potentially up to a sign. And that doesn't really help us create anything in superposition. So there's other kinds of operations that we could use for that purpose. And perhaps the most important one is called the Hadamard gate. And what this gate does is it starts with a 0 state and it turns it into an equilinear combination of 0 and 1. So an equal superposition between the two states. It does something similar as well to the 1 state up to a sign. So these are 3 really common, really important quantum operations, but they only allow you to do very specific things to states, whereas if we were actually doing quantum computation, we are going to need the ability to create arbitrary states. So there's a whole library of unitary gates that does that. You can get yourself from any state vector to any other state vector using some sequence of unitary operations. And there's an infinite number of them. This is like a continuously parametrized group. But generally, a quantum computer at a hardware level is going to be able to implement some of those gates really well. And we're going to want to express arbitrary gates in terms of them. And so this is one of the places where quantum software starts to play a really important role. So if you have an arbitrary operation that you want to implement, you're going to need a tool to actually find the sequence of unitary operations that's going to get you there. Not really something you want to do by hand, something you want the software to do. So in quantum computing, we have these qubits, we prepare them in some state, we apply some unitary operations. But at the end of the day, like we want to do a computation, we want to solve a problem, which means that we need some way of actually getting an answer out at the end of the day. So the final step is the idea of measurement. And again, this is something in quantum mechanics, if you've taken it, you're going to be familiar with. In a physical setting, this is again going to be something that is hardware dependent. One way of imagining it is like there might be a transition between like the 0 and the 1 state, and whether that transition happens or not, it's going to emit a photon. That's something you can observe. Again, hardware dependent. But mathematically, it corresponds to essentially sampling from a probability distribution. And what those measurement outcome probabilities are going to be are governed by the amplitudes of the state. So if you have a qubit in a linear combination of 0 and 1, If you then go and measure that qubit, you're going to observe it in state 0 with some probability given by the amplitude, the 0 mod squared, and the corresponding probability of mod squared beta for the 1. And you can see why these now need to sum to 1 is because we're measuring it, it has to be somewhere, therefore the probability is sum to 1. So a quantum algorithm, in essence, is a combination of these three things. We prepare qubits in initial state. Generally, it's going to be 0. We apply some unitary operations, and we take a measurement. And the idea is to do all of these things in a computationally meaningful way such that they solve a problem of interest. And so at the end of the day, you've done something useful, you have your answer, you've solved your problem. Now, generally, we represent this computation in a very specific way. Right now, it's a bit abstract, but like this is an algorithm, there is a logical flow to it. The language that we generally use to represent these calculations is that of quantum circuits. Again, if you've seen in a computer science course, like circuits in terms of logic gates, this is largely the same idea. In a quantum circuit, we have these wires here. They represent each a qubit. You can see we have some unitary operations here. We have a measurement at the end. So quantum circuits are the language in which we generally express quantum algorithms. But a quantum algorithm in and of itself isn't just a single quantum circuit. It's some quantum circuit, some quantum subroutine running as a component of a larger algorithm. And generally that entire algorithm is mostly going to be classical. So even some of the most quintessentially quantum algorithms that we think of as being able to solve problems really, really well, there's only some parts of that algorithm that are going to be quantum and the rest is classical, working around it with the outcome. And so that leads me to address one of the first common misconceptions about quantum computing is that people think maybe quantum computers are going to solve every problem exponentially faster. So that's not true. There are certain problems where we do know quantum algorithms that are going to work really well. And specifically, physics problems that are intractable on regular computers, quantum computers are going to help us with those. There's a lot of potentially very, very good applications of that. It's going to improve our understanding of physics. There's going to be applications in chemistry, biology, things that are going to propagate and have net positive effects on society. We also know quantum algorithms that have potentially more malicious applications like breaking the public key cryptography schemes that we have. We know a quantum algorithm, it's called Shor's algorithm, that is exponentially faster than the best known classical algorithm. Now, not every quantum algorithm, though, is going to be exponentially faster. Some are only going to be, for example, polynomially faster, and I'll show an example of that. It's called Grover search. And there's other potential applications for quantum computers in optimization and machine learning. So they won't be able to solve every problem exponentially faster, but there's enough of them that we know of that they'll be able to do very, very well, that it is actually worth building these machines to do that. But so far, we've only looked at the case of one qubit. It's this two-dimensional vector with two-dimensional matrices being applied to it. We're not going to get very far in quantum computing with only one qubit. We could simulate that classically. It's just a 2x2 linear system. In order to actually do something serious, we need more than one qubit, and we're going to need actually lots of qubits. So multi-qubit systems physically is going to correspond to many of these physical systems that are coupled or interacting in some way. And depending on the hardware, this might be like a physical coupler between two little circuits representing each a qubit. It could be electromagnetic pulses that affect more than one qubit at once. Again, it's hardware dependent. Mathematically, though, it corresponds to a matrix operation called the tensor product. So you can see here, if we have two qubits that are both sitting in state 0, by themselves, they have two-dimensional state vectors, but when you combine them, they have a system now with a 4-dimensional state vector. If we were to add a third qubit, we would end up with an 8-dimensional state vector. And so you start to see very, very quickly why we would actually need to build such a device instead of just simulating it. because the size of these systems does grow exponentially in the number of qubits. Now, to give you a sense of like how big these get, how quickly, the estimated number of protons in the observable universe is about 10 to the 80. And that's about the size of a qubit state vector with 266 qubits. So the computational space of these multi-qubit systems is just absolutely enormous. So in a classical setting where you may have started to run into memory problems, simulating large many-body systems, this is kind of just inherently baked in to the system of many qubits. This is a very, very big space that we can work with. Now, the bulk of quantum algorithms, it's not just a matter of like having a very, very big space to work in. You also need to be able to do stuff efficiently in that space. And that's going to involve, putting things into superposition and then doing something computationally meaningful. Now, the way that a lot of quantum algorithms start is by preparing a uniform superposition of all these 2 to the n possible basis states. This Hadamard operation that I showed you before on a single qubit, it takes 0 to an equal combination of 0 and 1. If you have many qubits and you apply that same Hadamard to all of them, what you end up with is an equal superposition of every possible configuration of those n qubits. So 2 to the n possible things. And what's really cool about this is because unitary operations that would then act on this state act linearly. And when things act linearly, they're going to act on each of those terms independently. So when you compute on something in a superposition of states, you end up with like a superposition of the outcomes of those computations. And that leads me to a second misconception about quantum computers that it really stems from this, is that there's this idea that quantum computers are going to solve hard problems faster because they compute everything at the same time. And it kind of looks like they do that because, yes, you put everything into a superposition, you apply a unitary operation, it acts linearly on all of those terms. But that's not necessarily going to help you solve a problem faster in and of itself. You still have to do something clever. Like there still has to, the algorithm still has to work a certain way. And a lot of that comes down to, even if you prepare this superposition, apply that operation, you still have to take a measurement to get the answer out. And measurements are probabilistic, so you're going to have to measure many, many times in order to actually get a result. A really good example of this principle is in an algorithm called Grover's algorithm. In Grover's algorithm, we're searching for an element in a space. And in the context of many, many qubits, you might be searching for one particular basis state of those 2 to the n possible states that is special in some way that's going to allow you to solve a problem. So just arbitrarily putting everything into uniform superposition and making a measurement, well, every state's equally likely, whether it's the one that you're interested in or not. You do still have to actually do something clever in order to make it more likely for you to measure the state of interest. And so Grover's algorithm works using a technique called amplitude amplification. It's a specific way of applying those unitary operations so that you boost the measurement outcome probability of the state that's the solution to your problem, while suppressing or decreasing the probability of measuring all the other ones. And Grover's algorithm is a neat example because it actually is a quantum algorithm where we see a speed up. It's not exponentially faster than the best known classical algorithm, but it is polynomially faster. We get something called a square root speed up. So this idea of superposition, of applying operations linearly to an entire combination of states, is one way in which quantum computers are different than classical computers. But it isn't just about superposition. There's one other important ingredient that allows us to do something fundamentally different, and that's the idea of entanglement. So we're going to look at a small quantum circuit here. So this is a little quantum algorithm. Imagine that we have 2 qubits now. They're both going to be starting in state 0. And we're going to apply a Hadamard to one of them. So the combined system at this point, we're going to have one qubit that's in an equal superposition of states and another qubit sitting in state 0. So we've done something to one of the 2 qubits here. But if we actually want to do quantum computing on more than one qubit, we are going to need operations that acts on more than one qubit at the same time. Some of those operations, though, are special in that they are called entangling gates because they do something very specific to these states. So originally we have a state where we can describe each of the qubits separately. There's an operation called a controlled knot. And a controlled knot is kind of like a conditional gate in that if the first qubit, called the control qubit, is in state 0, nothing is actually going to happen to the second qubit. But if it's in state 1, something will happen to the second qubit. And what happens is a NOT gate or a poly X. Now, when we apply something like that, it's something that's going to work linearly on each of the terms in the superposition. We end up with a state that looks like this. And you'll notice that I haven't written it here with a tensor product in between the two qubits. And that's because we can't. So this state is different in that it's entangled. We can't describe the two qubits separately. We can only describe it as this like 2-qubit blob of a state. And what's interesting about this state too is that the measurement outcomes are correlated. If we measure the first qubit and observe it in state 0, we know automatically, because of the structure of the state, that the second qubit's also going to be in state 0. Now, entangled states play a really important role in quantum computing, especially in protocols like teleportation, in which they're used as resources. The reason that some algorithms work is specifically because states are entangled. And that's where the third misconception I want to address is. If you look at media articles about quantum computing or quantum teleportation specifically, you will often see pictures of Star Trek. That is not what quantum teleportation is. Quantum teleportation is a quantum communication protocol that allows us to teleport or transfer the state of a qubit held by one party to the state of a qubit held by another party when two parties share an entangled pair. So you can see here that we have, this is a 3-qubit algorithm. We have 2 of those qubits starting in an entangled state. One person has one of them, the other person has another. And each of those parties really only has to do operations on the qubits that they have at any given time. There's a bit of measurement involved, some classical communication of those measurement outcomes. But at the end of the day, you can transmit a state that one person held to a qubit, potentially in another location, that is held by somebody else. And this is actually something that's been implemented in practice, like over large distances for communication purposes. So in a nutshell, that's quantum computing using superposition, using entanglement. We can do algorithms that are fundamentally different than classical algorithms. And in some cases, there are actually material speedups over the best known classical cases. But none of that has really addressed what it looks like to solve a physics problem on a quantum computer. So I have here the time-dependent Schrödinger equation. If you take in quantum mechanics, either your most favorite equation or your least favorite equation. So if you want to solve this Schrödinger equation, we can, given a Hamiltonian, we could figure out a way of essentially, given the state at some initial time, figuring out what it looks like as a later time by evolving it under this exponentiation of the Hamiltonian for a desired amount of time. So the cool thing about Hermitian Hamiltonians is that when you exponentiate them like this entire operator here has a very specific property. It's actually a unitary operator. And quantum computers apply unitary things. So if we have a system where we can, if we have a Hamiltonian, if we can find some sort of analogous Hamiltonian that's acting on qubits, that's going to act on the qubit system in the same way that the regular Hamiltonian would act on the initial system. If we can do that, what we call problem mapping, we can then evolve that qubit system under that unitary operation. So we can take this process here, where we figure out the state of the system at a later time. We can actually simulate that process on a quantum computer by evolving the corresponding qubit state under that unitary operation. So this is called Hamiltonian simulation. And this is the key way that we can simulate a physical system on a quantum computer. Now, how that simulation actually looks in terms of gates will depend on the hardware. And there's kind of a continuous spectrum of how you can actually do that. We generally make the distinction between something called analog simulation and digital quantum simulation. So a digital simulation is very much like what I described. You have some unitary operation, you want to turn it into like the sequence of individual gates acting on 1 and 2 qubits. You're kind of like discretizing it almost in a way. At the other end of the spectrum, you might have something called an analog simulator. Now, what that generally is it's a set of physical qubits that are going to just be time evolving under some continuously applied Hamiltonian in the same way. And both of these models can be used to achieve like universal quantum computation, to implement any unitary that you want. There's also kind of in-between cases where sometimes you might do continuous evolution for a little bit and then apply some discrete gates. This is going to be something that depends on your hardware. But the main idea is that you have to do problem mapping from whatever is your system of interest into an equivalent qubit system. Then you can evolve that qubit system, you can take measurements, and that's going to allow you to learn something about how your original system behaves. So this is something that people have actually done, and it's something that's very widely applicable in many areas of physics. I'm just going to highlight a couple examples here in particle physics as well as condensed matter physics. And this is where you really start to see how the pace of the field has accelerated over the last 10 years. So one of the seminal simulations that was done on a quantum computer was back in 2016, or probably 2015, it was published in 2016, is a simulation of lattice gauge theories. Now, if you remember back from slide 1, lattice gauge theories, simulating those, that was the thing that people made special purpose computers for. So quantum computers are a very promising platform for simulating these theories because they are large, they are computationally intensive, and they map pretty nicely to qubits as well. So back in 2016, one of the very first simulations, actually I think it was the first simulation of a lattice gauge theory, was done on a 4-qubit system. And it was a trapped ion machine. So we had 4 little ions suspended in an electromagnetic field. We're applying little laser pulses to them. That's what's applying our qubit operations. And what this simulation did was it simulated a one-dimensional set of lattice sites upon which these were modeled as essentially whether or not a qubit was in state 0 or 1 represented whether or not a system was like in a vacuum state or had a positron there or had an electron there. And they were able to simulate a very, very small model that showed essentially the creation of like positron-electron pairs. Now, this was a 4-qubit system. It used about 200 quantum gates, which, given the time and the technology at the time, is actually amazing. And they were able to get results on this that really matched the theoretical model. So this was almost 10 years ago now, a 4-qubit simulation. Fast forward to about 2 months ago, a very similar simulation was done on a different type of machine, so not trapped ions, something called superconducting qubits. This is a machine that is made by IBM. It has, I think, 127 qubits. They used 112 of those to do a much larger scale simulation. So it wasn't just 4 qubits and 200 gates. They were doing something like 14,000 2-qubit operations. So this is a seriously impressive simulation at scale. And 112 qubits, this is very, very big. This is a state vector with 2 to the 112 elements in it. So this is something that's starting to become, or probably is, actually quite intractable on a regular computer, and we're going to need a quantum computer to do this. So you'll find lots of examples in particle physics of how you can map those problems onto quantum computers and then simulate the time evolution of those systems. Another area that's hugely benefited is condensed matter physics or material science, simulation of actual materials. And this is where those more analog simulators come in handy because you can set up these arrays, these 2D arrays of atoms that are representing qubits, and you can see how those evolve over time. And a couple years ago, there were some really interesting simulations that were done on neutral atom simulators, which correspond to loading up these 2-dimensional arrays of atoms. They were actually able to observe different phases in those systems than you would be able to see classically. So the three things that I've just showed, we had two particle physics examples and a condensed matter example. You might have noticed that those were all on different types of quantum processors. We had a trapped ion machine, we had a superconducting qubit machine, we had a neutral atom machine. Those are just three ways that people have made quantum computers. Over the past 10 years, people have been exploring a lot of different kinds of architecture. So those are three of the more advanced ones, but there are also ones based on photonic qubits, on spin qubits, on various kinds of superconducting qubits. Like every company that makes superconducting machines, they have like a different way of actually creating and operating those qubits. And this is something that, they've been able to scale many of these technologies very large. So we now have quantum computers with over 100 operational or over 1,000, operational qubits. I have to keep updating this slide every time I give a talk because things are changing very fast. So the scale of these machines is absolutely enormous now. Remember, 266 qubits gave us something that was 10 to the 80 in size, number of protons in the observable universe. So these things are massive, and there's a huge amount of potential for them to do very interesting things that we definitely wouldn't be able to do classically. So that brings me to another misconception, maybe. That's why I put some question marks, because this is something that's very much an open question and up for debate. And it's also something that's just constantly changing over time. So given that we have these machines with 1,000 qubits, the computational space is just immense. Are today's quantum computers better than classical computers? So people have been trying over the last couple of years to demonstrate this. And it's been called many different things. Sometimes it's called quantum advantage. More recently, it's been called quantum utility. But can we actually get a quantum computer to do something that is provably something a classical computer cannot do? So photonic processors have been used to demonstrate advantage, superconducting qubit processors as well. One of the most recent simulations of this was actually just about 8 months ago on a 127 qubit superconducting qubit machine. They said, we did this simulation on this very, very large device. There was no way that we could do this classically. So it turns out, though, that one of the best ways to advance classical computing is to claim that you had a quantum computer do something that a classical computer couldn't do. Because as soon as you make a claim like this, you'll see a preprint materialize on the archive a couple days later saying, oh, well, using this very specific tensor network method, we were actually able to do that computation on a laptop. So this is very much a moving target. And whether or not something achieves quantum utility or not is still up for debate. I think we definitely have seen instances of quantum computers doing something that was classically intractable at the time. But again, classical methods have improved. But you also need to ask yourself the question of whether or not that was a useful problem. If you're just kind of running random circuits that scramble things up a bit and you sample from the probability distribution, that's not nearly as compelling as being able to simulate an actual physical system that has a meaningful real world application that you couldn't do classically. So part of the reason that today's quantum computers, even though they have 1,000 qubits, aren't as powerful as they could be, is that they're actually quite noisy and there's a lot of constraints in their operation. So especially in things like superconducting computers, there's constraints on which qubits can actually talk to the other qubits. So this is an example of a 7-qubit device where you can see that not all of the qubits are connected. And they're all different colors because they all have different error rates. And different architectures have different constraints. Trapped ion architectures, for example, generally you can have any two pairs of qubits interact, but then the gate operation times are going to be longer. At the same time, the coherence times are longer though, so there's a trade-off. And comparing quantum computers is actually really, really hard because it's not just about qubit number. You could have 1,000 qubits, but if the error rates are like 2%, you're not going to actually be able to do anything useful. So when you compare to quantum computers, you have to also look at things like speed, at the error rates, at coherence times, even at how good the software stack is, because right now you really need to have good software that's co-designed with intimate knowledge of your hardware in order to extract good performance. So boiling all of this down to a single number metric is really hard. And we can't really even agree on what metric to use. Like every company that makes a quantum computer has a different metric that they are conveniently the highest at. So that all said, like we are very much still in the early days of quantum processors. If you look at what classical computing looked like 70 years ago when we had machines with vacuum tubes versus the integrated circuits we have today, this is a massive amount of progress. Similarly, we have superconducting qubits today, but what qubits are going to look like in 50, 60 years, we really don't know. It could be one of the architectures we have today. It might be something completely different that we haven't even thought of yet. And in a similar vein, what classical computers look like 70 years ago, room-sized machines that took a team of people to operate. Quantum computers right now are currently quite large and take a room full of people with PhDs to operate. So there's a lot of progress that still needs to be made in order to actually get these machines running physics applications up to scale. And even though we have them, like we need to think critically about what problems we should try to solve now and in the near future, but also how those problems map efficiently to algorithms, and furthermore, how those algorithms map efficiently to hardware. Because if you can't map your problem efficiently to the hardware and actually run it, it's not going to be super useful. And that's where quantum software plays a really important role. So I define quantum software as basically any kind of software that enables us to express and execute algorithms that can run on quantum hardware. And I say can because it might be quantum software that it's only used for simulation, but it's still simulating a quantum algorithm. But this also includes things like compilers, the high and low level frameworks, down to the software that allows you to control those individual electromagnetic pulses that get applied to qubits. Now, in classical simulations, probably many of you program. When you've programmed, you've written an algorithm at a high level, you've pressed a button, and it's run on your CPU. That is owing to many, many decades of compiler engineering. You don't have to worry really about how to optimize your code that much unless you're working like at the really, really low levels. The compiler is going to do that for you. Eventually, quantum computing is going to look like that, I hope. But right now, there's a lot of work that has to be done manually in between in that process. And that's something that my research group works on. It's how to build good and efficient quantum compilers. Because in order to actually run something on these devices, like you've seen that these things, they apply unitary operations. If you have an arbitrary line of code, it's probably not clear how to turn that into a unitary operation. And that's the role of the quantum compiler. So even if you have a quantum algorithm that I've actually shown Grover's algorithm here, it looks just like normal code, but the actual operations that run on the quantum device have to go through this very involved sequence of steps that decompose down into 1 and 2 qubit operations. So this is very much not something that you want to do by hand. You want good software for this, especially if you're going down to the pulse level. So the entire quantum compilation stack, going all the way from us down to the hardware, is something that we need effective tools for. A lot of that work is still done manually. And I want to highlight an example of that. And this is in the last, I might be a little bit over time, but in the last 5 or so minutes of my talk, show an example of a real physics problem that we did use a quantum computer to solve, where a lot of the work, again, was in the problem mapping and also in that process of getting us from the algorithm to the hardware device. So this is work that was done in collaboration with some nuclear theorists. And we looked at how to predict the neutron drip line in oxygen. So this is a nice problem because it's quite easy to explain what it is we're trying to do. Let's say we have a nucleus with some number of protons and neutrons in it. We can have isotopes of that nucleus. We can add neutrons. Generally, the binding energy of that nucleus is going to go down. The energy is going to be lower. It's going to be heavier. We can add more neutrons, but eventually we're going to add 1 neutron too many, and this thing is no longer going to be stable, and it's going to decay. So the question of the neutron drip line is how many neutrons can we add before this thing decays, before it becomes unstable? And while this is an easy problem to specify, it's actually quite a hard problem to solve both theoretically and experimentally. In 1999, they figured out what this point was for nitrogen and oxygen, but it wasn't until 20 years later that it was confirmed for the next two chemical elements. And even more recently, like there have been some predictions, there have even been some experiments where we're pretty sure we know what it is for sodium, but that's kind of it. We don't know the answer to this question for the remaining many elements in the periodic table. And that's because both the theory is hard. This is solving essentially the quantum many-body problem. This is computationally hard. And there's also different theories that disagree on different elements, which is kind of interesting. But even if we wanted to solve it experimentally, you need these large special purpose facilities where basically they shoot this giant beam of particles at a target and look at what comes off. And the things that come off have very small half-lives, they decay very, very quickly, and there's very few events observed. In the case of sodium, we've only seen 10 of those sodium isotopes like ever across 2 experiments. So this is a nice problem, very good candidate for using quantum computers. So the question though is how to actually turn that into a quantum computing problem. And I'll go through this a bit quickly because I know I'm a bit over time now, but essentially it involved a lot of problem mapping. We thought about, okay, there's these neutrons around this nucleus, where can they be? For each of those places that they can be, we're going to assign a qubit. And whether or not that qubit is in state 0 or 1 is going to represent whether a neutron is there or not. But then it's a matter of mapping this to a problem. We want to find the binding energy. And essentially, we want to find the ground states of those systems of many qubits. So we have to figure out which terms in the superposition need to be there in order to construct the ground state. And then we need an actual algorithm that's going to help us find the ground state. We used one called the variational eigensolver. Essentially, we made little quantum algorithms that were parametrized in some way. We tried to prepare things that looked like the ground state and then optimized to try and find the parameters that actually did so. The issue is that the very first iteration that we did, well, the circuits were enormous. They needed like 1,000 2-qubit gates to do for some of the isotopes that we looked at. So that was where we ended up doing a lot of problem size reduction through something called qubit tapering and a lot of very, very manual circuit optimization to make those quantum algorithms smaller so we could actually run them. So we solved the problem classically, but then we did actually run it on hardware for a very specific case. And we actually were able to extract meaningful results out of the hardware. You can see here that for one of these isotopes, the binding energy was the lowest, then it increased for the next isotope. That was the drip line nucleus. But again, there was a huge amount of problem mapping that I'm kind of sweeping under the rug in order to get to this result, and also a lot of something called error mitigation that needed to be done. But this goes to show that you actually can use a quantum computer today to solve a physics problem. Now, moving forward, though, of course, there's lots of challenges. We're writing software for machines that are changing over time. They haven't reached their full potentials. We have to write software for algorithms that we haven't even invented yet. We don't actually know a lot of quantum algorithms. So how to write good software is very much an open question. Furthermore, these machines are noisy. So how are we going to deal with noise in the future? So one of the most important things in the next few years, and you're going to start to see a lot of this, is how to actually do fault-tolerant quantum computing. In fault-tolerant quantum computing, we have error-correcting codes. We have many physical qubits working together to form a logical qubit, the idea that that logical qubit has overall lower error than the physical qubit. But when you start needing thousands of qubits to represent one logical qubit, you start to see even like bigger software challenges because somebody has to write the software that's going to compile those many thousands of qubits of algorithms. That's going to be very challenging. So even at that stage, we're still going to need a lot of qubits because of that. So these are just a couple resource estimates to give you a sense of, yes, even though these problems are classically like intractable, they're still going to take potentially quite a long time on a quantum computer. So some of these physics problems, estimates for even like 100 spins in a system running in those error correcting codes, might take hours. Factoring numbers, breaking cryptography, we have estimates on the order of like days to years with millions of qubits. So just because we're using a quantum computer, it doesn't mean the problems still aren't big. But we're constantly seeing improvements in both the software and in the hardware, and things are looking more and more scalable every day. But there's still a lot of work that needs to be done improving both. So very exciting time to be in the field. There's a lot to do. And hopefully this gives you a sense of what it's like to actually use a machine like this to do physics. So thanks for your attention. And thanks also to my collaborators on my nuclear theory project, as well as to Microsoft, who actually gave us the hardware credits to run those simulations. And very happy to discuss anything related to quantum computing and take questions now.
Wonderful. Okay, thank you very much to Dr. Di Matteo. And I'm just going to bring up some questions. I really enjoyed both hearing about the basics of quantum computing and also hearing the most recent applications for physics-based problems as well.
The very bottom. You're looking for start video.
Thank you. Okay, so I'm just going to open things up for questions currently. We have an audience here as well at Mount Allison. So maybe I'll just start by checking with our group here to see if there are any questions from the audience in the theater. People can keep thinking of those, and maybe I'll just start with a question here as we get going. So I was wondering, it's always difficult for looking at how current research is going to eventually lead to application down the road, and that's one of the most interesting things about physics research, I think, sometimes, is just knowing where things are going to go. If you were to look way into the future, so if we went beyond the 10-year time frame to maybe the 50-year time frame, do you have any speculations for where we might be going with quantum computing in the distant future, either in terms of physics applications or general life? Are there areas you would see unfolding down the road?
Yeah, there's lots of potential applications. Like on the fundamental physics side, the simulations of like gauge theories, understanding like fundamentals of nuclear structure, I think those are really interesting applications. But on the more like, everyday scale, like a lot of the examples in physics and simulating these systems has applications in like designing new materials, designing new chemicals, which, if you propagate that further, has potential applications in health, like looking at what like compounds or chemicals are going to be good for like specific applications in pharmaceuticals, for example. So there's potentially applications with like actual real world societal benefit that we might be able to see at a much later date. There's other potential for using these things to simulate, again, like very far down the road, like evolution of systems, for example, like where there's a lot of turbulence. So for example, like ocean and climate science and weather, those are maybe a bit more speculative, but still potential application areas. Finance is another area where people have looked into using like quantum computing to either simulate the behavior of the market, or more, actually people are already doing this today to like solve optimization problems for like how to balance a basket of stocks that you're buying. Let me think, what else? I think the physics ones are really the most interesting though, but that's why I'm here as a physicist. So.
Wonderful, thank you. Yes, and I was wondering too about weather forecasting. As you mentioned, I mean, it's very good right now, but could quantum computing make it even better in terms of timing?
Yeah, I think there is potential for that as well. Unless you're in Vancouver, and then you're pretty much better off just guessing that it's going to rain, like at any given time.
Okay, I have an online question, and people can continue to post questions online as well. But the first one is, are there agreed upon benchmarks for quantum computers in terms of comparing them? And who agrees or makes those benchmarks?
I'm really glad somebody asked that question. I actually have a slide about it. If I can find it. I'm not sure if you can still see what I'm sharing.
See it here.
Can you see my slide here about comparing quantum computers?
Yes, I've got
Okay.
it here.
Yeah, so there's a couple different metrics people are proposing. A lot of them have actually been proposed by companies, but one of the most common ones you'll see is something called quantum volume. And so this is a very specific benchmark that is basically categorizing like how well a quantum computer can solve a very specific problem with like statistical significance. So it's like how large of a square circuit can you solve, where square refers to like some number of qubits, some amount of depth in a circuit. It's essentially a random circuit. It just kind of like scrambles stuff up, and then you sample the output and ask whether the samples that you got pass some like statistical threshold or not. So volume in the sense that it's like this square. But then even how that gets like reported, so this is originally something that was proposed by IBM, how it gets reported is different depending on who is doing the reporting. So some companies will just like report the number of qubits, whereas others will report like 2 to the number of qubits. So it looks like they've got this quantum volume of billions, where really they just mean it's like 18 effective qubits, where they can do a circuit with like depth 18. So that's one of the common metrics. There's other metrics for speed, and there have also been some more recent holistic ones that try to look at both and also try to factor in errors. But again, they are all different, and I don't think any company really reports all of them. They tend to just report like the one that either they made or that they are good at, or most typically quantum volume would be the one that you see.
Hey, wonderful, thank you. I had another question come up online, which is, are there any implications to having an AI as it evolves in terms of interacting and learning with a quantum computer that is program writing or encryption break?
Yeah, that's a very good question. Right now, a lot of quantum programming is done manually by humans. We don't know a lot of quantum algorithms. So we haven't started really looking too much into like whether an AI could potentially learn its own quantum algorithms or learn how to write them. I know there is some work happening in that direction, but I'm not super familiar with what's happening. In terms of breaking encryption, we do already know what that algorithm looks like, but it is a matter of like getting it down to a practical level, because you can kind of see here that the resource requirements for doing it at scale are actually quite huge. But like one of the areas that my group is looking at is how to apply machine learning techniques like for circuit compilation. So like once we do have an algorithm that big, can we use machine learning techniques to optimize it? So that's one particular area where like machine learning and AI tools could potentially be a benefit. But then that's a malicious application. We're more interested in using those tools to like optimize Hamiltonian simulation circuits to make our simulations better.
Okay, thank you. And I had another question online, and I think we'll make this the last question for you today. So the question is, along the lines of an earlier point, who decides who will write the fault detection software? And will there be, or are there already, large collaborations in high energy physics for such tasks?
By fault detection, would that be, I guess, fault tolerance?
I
Uh,
think so. Yeah.
Okay. So there's not too much in the way of like the fault tolerant compilers right now. Like there are some that exist for very specific error correction codes. I think they're mostly coming out of universities and industrial collaborations right now. But like a lot of the large like high energy physics projects, like for example, CERN, like quantum computing is something that's on their horizon and that they're looking into, but more I think from the physics application and problem mapping side rather than like the lower level compiler side, which is more where I'm sitting. I'm not sure if that answers the question. Happy to follow up.
Okay, wonderful. I think that is perfect place to finish in terms of our question period. So thank you again, Dr. Di Matteo, and I'm just going to turn it back over to Dr. Peter Poole.
Okay, good. Yeah, so I'd like to, as I said before, I'm Peter Poole from St. Francis Xavier University, Regional Coordinator for this year's CAP lecture tours. At this time, I want to thank Gwen Grenier, our National Coordinator for the CAP lecture tour, the staff at the CAP office, and our host, Professor David Fleming, for helping to organize today's talk. And of course, thank you to Dr. Olivia Di Matteo for a really clear presentation. Thank you all for participating. We also want to thank the CAP Foundation and its generous donors who have made the CAP lecture tour possible. To all of you, please consider making a charitable contribution to support this program and many others. And also, I strongly encourage everyone to attend the CAP Congress to be held May 26th to 31st at Western University. Our next talk will be by Professor Ben Newling on Thursday, March 7th at 12:30 Eastern Time, who will speak on, the title of his talk is Some Notes on Musical Acoustics. I hope everyone can attend. As a reminder, all participating students online and in person are invited to remain to have an informal discussion with Dr. Di Matteo, and online participants may now unmute themselves and turn on their videos. Have a great day. Thank you. Merci à tous.